Well, here we are at the physics video lecture. Psci 168 video lecture 15. So we're talking about the Arizona meteor crater, and I went out and looked up the relevant information. Maybe you guys did the calculation, but I'm going to do the calculation now, so we'll all be caught up on it. So let's set this thing up again. If you looked it up, you probably want to take a road trip out there and inspect the thing sometime. It's in private hands, so you'd have to pay admission and take a tour and stuff. But let's have a look at what we're talking about here. The meteor crater, it's called the Barrington crater. There it is in Arizona, and it was excavated by a gigantic impact. So what we did was we modeled it as a hemisphere of radius r. Now, in fact, it's not as deep as it is. The depth is less than the radius. That doesn't matter though, because we were just doing an approximation here. We had 1/2 mv squared, where the asteroid or the meteor was coming in with this tremendous speed. Impact. When you read about it, you find out that the thing was vaporized on impact and so forth. A really interesting discussion there. So what we did was we equated this with, I'll use a different mgh, the work done to lift all of that mass out of the crater. And we had to make a bunch of interesting simplifying assumptions. So what we ended up with was this thing here, this meteor came in, it had a radius r. Okay. So it's a sphere of radius r, and this is a hemisphere of radius capital R. And we derived a formula. I'll just write what we ended up with. R, radius of the meteorite, or of the meteor, was equal to G R to the 4th over V squared, all to the 1/3 power. So there were simplifying assumptions there, because actually most of that energy is going to be converted to heat. And like I said, it's not as deep as the radius, a bunch of other stuff. Another point was that I said, let's let the densities of the Earth and the meteorite be the same, but this is an iron nickel meteorite that's a meteor that's much more dense than the rock of the Earth there. Nonetheless, these simplifying assumptions allow us to get this formula, which has what we call the correct scaling behavior. It's going to be proportional to this, and there would be some small or greater or smaller factor in front of it. Okay, but this would be the basic dependence on these fundamental quantities here. And this is good here. I could write here plus heat, and we'll talk about heat later on. Okay, so what did we find when we looked up the data for this thing? They told us that the diameter was 3891 feet. D equals 3891 feet. Impactor diameter about 50 meters, depth 560 feet. I'll just write depth. This is the diameter, depth 560 feet. However, there's a bunch of rubble in the bottom, okay, that fell back in. Okay, be that as it may, this diameter here turns into a radius, capital R, of approximately 593 meters. The 3 is not important. The impactor is what they call it. They give us a diameter of approximately 50 meters, so we've got a radius approximately 25 meters. So this is what they tell us over there at the Arizona Meteor Crater website. Also a good wiki page. Wikipedia has an interesting article on it, and the private company has an interesting website as well. Okay, so there's a lot of good information on it. So this is the 593 radius meters. Make sure we write that meters because we convert it to metric system. We do all of our calculations in the metric system, and we also have, we're using G, 9.8 meters per second squared. Of course, we know that. And we used V, 10,000 meters per second. And that's a very good number because the escape velocity from Earth is about 11,000 meters per second. So if something comes in from the far reaches of outer space, it basically has to have this much speed, okay? There's really no getting around it. Maybe you could have more, but not a lot more necessarily. So that's a really good number. Good, so what we do is we plug in here, and I'll just give us the results, some of the numbers that I put in. So I get R is equal to, I put in my 9.8 here. This is all metric, so you have to put in the right scale. 9.8, 593 to the fourth power. The fourth power divided by 10 to the fourth squared, right? So that's 10 to the 8th. And the answer is going to be in meters. And I have an intermediate one. I end up with 1.21 times 10 to the fourth. We get some good cancellations here. Okay. So I'll just write down what I end up with. I end up with 23 meters. That's much better than I would have expected. Okay. And right. So the experts over there, who knows what they were thinking, but if they were basing their estimate on these physical principles, and those are the physical principles, then you'd expect to get something in that ballpark. It could have easily been, 15 or 40, but we did land right there on that official estimate, just with the things we did. Okay, so this is a good example of the transformation of energy. And that's what the next topic is going to be. It's our next major topic is referred to as conservation of energy. So this was a great example. I hope you guys, at least some of you, gave this a try. Once again, you have to take this to the 1/3 power, right? Cube root. So 593 to the fourth power times 9.8 divided by 10 to the 8th power, and the whole thing to the 1/3 power, you get your 23 meters. So this again was an example of the transformation of energy from kinetic energy to work in heat to the degree that it could leave a big crater in the ground. So this next topic is called conservation of energy. Now we're just working with estimates here, but the principle, which I'm going to go back to real basics for, the principle states that this amount of energy here actually has a strict equal sign with everything that happened on the right side. So the work that was done, the rocks that were shattered, the rocks that were fused, right, the heat that was generated, all of that thing would actually have a true equal sign. And if you said so many joules on this side, you would have so many joules, exact same number on the right side. So that would be the principle. We're going to work our way up to that. So first of all, just to remind you, energy is neither created nor destroyed. Created nor destroyed. It changes form. Okay. It changes form. So this meteor crater is actually a very rich and sophisticated example, and we can only use it loosely. Okay? Loosely speaking, gives us a great approximation, but we have to go back to mechanical energy. Okay? We're going to ignore thermal energy altogether until later on this semester. Oops. Okay. So for mechanical energy, we really know two kinds: kinetic energy and potential energy. So kinetic energy is always of a form, some kind of 1/2 mv squared. And if you have a lot of little constituents, a lot of things flying around, there's a whole lot of 1/2 mv squared. Okay, that's kinetic energy. Then there's potential energy. And there are a couple of different kinds. So the first kind is gravitational. And for the gravitational potential energy, that's the one we were using here, mgh, mass GH. Doesn't matter what letter you use right now, it's lifting something up. There are some other kinds, elastic potential energy. Actually, so since I have I'll just put that right under there. Elastic. This is when you stretch a spring, when you compress something, when you twist something and it springs back. Okay. So I'm not going to give us any letters or a formula for it, but things that are stretched or compressed, if they can spring back, then they have elastic potential energy. And in fact, if you have an old wind-up watch, who has that nowadays? Maybe someone has one. If you have an old wind-up watch, there's a spring inside, you wind it up, it'll run for a day or a week or something. So stretched or compressed springs, etc. That's elastic. Gravitational, of course, our grandfather clock had gravitational potential energy. Now, when we say energy is neither created nor destroyed, we mean that this energy, kinetic energy can change form into elastic energy, to gravitational energy. But in this mechanical set of phenomena, it just changes back and forth and back and forth, okay? So let me give a couple of examples for this. Well, it doesn't have to change back and forth. It can actually also run down, but we have to be careful. So, since we've talked about the grandfather clock, we have to, that's actually a tricky one. We have to make sure we clarify that. So my examples are going to be, first of all, the grandfather clock, and then I have a couple more that are actually related. So the grandfather clock, the work is raising, remember we said we wind it up or we raise those masses somehow. What does that get converted to? MGH is to raise, the masses, we wind it up, where does that energy go? You could say, well, the work it does is to turn the hands of the clock for 7 days. All the while, our mass is lowering. Okay, so here was our clock, and this mass down here, we wound it up to here, and then of course we have the pendulum swinging back and forth. So that H, as the mass drops over the course of the week, that's the work being done, turns the hands of the clock, all the gears, etc. But in the final analysis, it actually, since the clock ends up where it started, say, at this time, 7 days later, and this mass has gone up from the top to the bottom here, there was actually friction. So it actually did get converted to heat, okay, to heat and wear and tear. So heat, comma, by way of friction. So this is an example that isn't yet the pure mechanical one we're after, okay, but we have to talk about it because the energy was not lost, it was not destroyed, it turned into heat, and that's a later subject in the semester. The second example is of a simple pendulum. This is the one that really illustrates everything that we have to talk about here. We've talked about the simple pendulum before. Let's go ahead and talk about the simple ideal pendulum. What's ideal about the ideal pendulum is there's no friction, it never stops. Okay, it would just swing back and forth forever if there were no friction. So the simple ideal pendulum oscillates forever because there's no friction. Because no friction. So that's an idealization. Well, let's go ahead and draw it right here. Let's just draw a simple ideal pendulum. Okay. There's the mass, there's the length. This is where it's attached to. Let's give another color here. This is how it swings. Okay. And we got to make a nice, decent sized drawing of what we're going to show here. See, we have a lower level, lowest point, and we have this point here, and I'll even draw a slightly higher point as well. So we have a third point right here. Okay. So suppose we release it point 1, 2, 3, 4. Now this is the important line you want to draw horizontally. This horizontal line is the highest point that it can achieve. Okay. 5. And then it's going to swing back. And we have a really great demonstration that we do when we're together in this room, because this pendulum will never swing higher than the point we released it from. We're not giving it a push, we're just letting go. It falls, swings, it picks up maximum speed here, slows down, comes to a stop here. When it swings back, you can actually stand here against the wall and watch it come at your face. And it'll stop right in front of your nose, it won't hit you. Okay. If you released it in front of your face, swings away, comes back, because we have one that, we hang it from the ceiling. Okay. It's actually something everyone should do. It will not swing back to a greater height than it was released from. So if we're going to label this thing, we could say, I'm going to say release from rest, very important at 1. So we're releasing it from rest, makes the maximum height over here, it's the exact same height or less because there is some friction, but the ideal one has no friction, then it comes back. It just repeats itself. So what do we have here? At 1, so 1, it's all potential energy. Okay. At 2, it's picking up some speed. We can say potential energy plus kinetic energy. At 3, it's all kinetic energy. At point 4, it's some kinetic energy plus potential energy. And at the 5th point, over at the other side, at the original height that it has reached, it's all potential energy again. So this is what's going on in with mechanical energy. It's just cycling through, and then on the way back, same thing. So the ideal pendulum is just going potential to kinetic to potential and back and forth. That's energy conservation. So that's such a fundamental law, we really have to drive it home. What would be a violation of that law? A violation of that law would be if I release it from rest and it's higher when it comes to the other side. If that were the case, when it swings back, it would be even higher. It would swing itself from lower to higher amplitudes. Okay, that would be a violation. It's never going to happen. But that was not understood historically until relatively recent times. So there's a period where mechanical devices were being built, energy was being harnessed, water wheels were harnessing energy, and yet people were trying to get things to swing higher, so to speak. Trying to design perpetual motion machines. Okay, so this is very, very important. And then it was released from rest. Let me make sure I write that clearly. So release from rest at 1. In other words, do not give it a push. Okay, let me consult the clock here. Okay. Yeah, very important. Another example, my third example is really almost the same thing. So I've talked about the pendulum. This is the classic example. You really want to understand this. And see, if it swings higher, I release from rest, it swings higher, keeps swinging higher, then energy is coming into being out of nowhere. Okay, it's being created because each time, from this baseline here, you say, okay, I have mgh in potential energy. Hey, let's write that down. Let's label this picture before we move on. Label it a little bit more. So it's mgh, right? This mass has mass m, and the h that I'm talking about is the height above its lowest point. Okay. That's how much it has. Okay. Now, this kinetic energy down at the bottom where it's full speed, we can say that's 1/2 mv squared, but that is still exactly mgh. Okay. And the same mass, by the way, same mass. So, if I use different masses and letters in different circumstances, don't be thrown off by that, and so forth. And then down here again, because it's the ideal one, it's mgh. Now, in reality, it always swings a little bit lower, and eventually, if you wait long enough, it comes to a dead stop. Okay. Okay, good. So that was the second example. The third example is just an ideal bouncing ball. Okay. So example 3, and these have to convince you. So it's ideal bouncing ball. And really the same mathematics that I just wrote down holds true here. So here's an ideal tennis ball. Here's the ground level, ideal ground, IH. Okay. So if I release it from rest right here, it's going to bounce, and if it's ideal, it can come up to the same height. In reality, it's going to be somewhat lower. The ideal case, it can reach the same height, but it cannot go any higher. If it went higher once and it dropped again, it would go even higher a second time, and it would start bouncing from low and just keep going to high. Okay, so that would also be a violation of energy conservation. The energy we have now is we have here at 1, we have mgh. Right before impact, half mv squared. I'll name this one too. And back up to here, mgh. Okay. So that is the transformation of energy from potential to kinetic to potential back and forth. So here's something you can look up. Say a couple words about it. The perpetual motion machine. First of all, the perpetuum mobile of the first kind. And that's perpetual motion machine. The whole history of schemes to develop something like this. It's a machine that just runs on its own and actually delivers useful work in the bargain. So not only does it run forever like this ideal pendulum, but it does more than run forever. It actually allows it to do some work, which means in the case of my ideal pendulum or bouncing ball, it has to be better than that. It actually has to bounce higher than the point you released it from. And that's really what all perpetuum mobiles are trying to accomplish. And they cannot exist. They're ruled out. Okay, so conservation of energy means perpetuum mobile of the first kind. Later on we'll talk about the second kind. They're both impossible. Good. So is impossible. It violates conservation of energy. Now I'd like to show have some interesting slides to show you guys, but what I'm going to do is email them to you, okay? And you'll print them out and put them in your notes, and I'll discuss them a bit next time. Violates conservation of energy. Okay. Cannot be overstressed how important this section is right here. So I have two images to print out, and I'm going to send them to you. I'll email them to you, and you can print them out. One of them is called Water Crane. And the second one I think is titled Perpetual Motion. Have to check that. But you want to print them out and add to your notes. They're old woodcuts. They're actually images. One of them is an idea that someone had, a perpetual motion machine. And the other one is actually a sketch of real water wheels being used to do work some hundreds of years ago. Enormous machines. These images are actually really interesting to go through because you have to tease out what's even going on in them. They look kind of complicated. However, you guys print them out, and not only print them out, but take a good look at them and try to analyze them and see what's going on. So the water crane is principally okay. It's a picture of a big giant water wheel that was being used to lift buckets or something. The perpetual motion machine is principally flawed, but it's really interesting to pursue all of the little gears and the water wheel powering the gears and so forth. So here I'm going to say, explain the problem. Why can it not work? Okay. So this section is really important for the principle. We're actually going to pursue the water crane version because we have a major central part of our entire semester is hydropower, which is coming right up. And so water wheels are an original form of hydropower. And we're just going to start with the really basic version there. Good, so that counts as homework. You want to make sure as soon as I send these to you that you print them out, add them to your notes, and let me consult here. Okay, yeah, I think this is a good place to stop. Have a good look at these things. Just to review, the Meteor crater you may want to have another look at, really interesting topic. We're reviewing the grandfather clock and the simple pendulum, and this principle that when you drop something, it's not going to bounce higher than from where you dropped it. Same thing with the pendulum here. Those are important conservation of energy examples. So once again, conservation of energy, what it means. So at this point, you know we're not talking about saving electricity by turning the lights off and that kind of thing. Okay? This is a different type of conservation of energy. In fact, maybe I should say one more thing. When we talk about these conservation laws in physics, it means something stays constant. So when I said energy is neither created nor destroyed, it's staying the quantity is staying the same. So conservation law means constancy. Okay, I'll have a chance to explain that again, but you may want to put that down right now. Conserved means constant. Here, I'll write that down. Short note. Conserved means constant, unchanging. Okay, so conserved means constant. Okay, good. We'll see you guys next time.